Before we begin this presentation, let's just remind ourselves about the 3 steps of proof by induction. So here they are. Oops. The base case, verify that the result is true when n is equal to 1. Then the second case is the induction hypothesis, and for some arbitrarily fixed value integer k, which is greater than or equal to 1, assume that the result is true for all integers. Okay, so essentially you're just making a statement there. Stating a hypothesis. The last step is use this hypothesis that you just come up with, that the result is true, to prove that the result also holds for when n is equal to k plus 1. So there is 3 steps there: a quick verification, make a statement, and then a calculation. Now that is grand. Now I just skipped over some summations there that are not relevant to what I'm going to do now. So calculate the terms u3 and u4 for the sequence defined by n greater than or equal to 2 by the recurrence relation u of n plus 1 equals un plus 3 times un minus 1. What we're going to do here is first off set up a sort of grid. Let's put it in green. Now, whoop, meant to drop line there. Start again. Draw a grid. Essentially a very structured approach helps here. Now we'll have n is equal to 1 here, n is equal to 2, n is equal to 3, n is equal to 4. So what we're interested in is u of n plus 1, u of n, u of n 3 times u of n minus 1. Okay, so we'll set up our grid like that. Actually, we don't need it there. We don't need that one. So first off, let's do for u of n we're told that start off with n is equal to 2. Okay, so here, and we know that u2 is equal to 4. 3 of un minus 1, that's 3 times the previous one, so this is 3 times u of 1 is 3. 3 times 1 is 3. Add them together, you get the next one, u of n plus 1. So when n is 2, n plus 1 is 3, so u3 is equal to 4 plus 3, and that's 7. So let's do it for the next line. U of 3 is equal to 7. What is 3 times u of 2? That's equal to 3 times 2. Sorry, 3 times 4, and that's equal to 12. Just make a quick note of that. 3 times 4, 3 times 1. Okay? And add those two together, we get u of 4. And that is equal to 19. We'll do it for one more. We're not actually asked for any more, but I'll just do it for one more. U of 4 is equal to 19. 3 times u of 3, that's equal to 3 times 7, that's 21. Add those two together, we get u5, and that's equal to 40. So that is calculate the terms u3 and u4. Okay. Now, the next step is, for each of the following sequence, find a recurrence relation that gives un plus 1 in terms of un. Okay, so what's happening here? That is un plus 1 is, first off, u0, let's say u1 is 12. u2 is 1.2. So u2 is equal to u1 divided by 10. Okay. Likewise, you go on to the next one here, u3, that is equal to u2 divided by 10, and so on. So what we could say here is that u of n plus 1 is equal to u of n divided by 10 with initial condition, and never ever forget to put in the initial condition. Oops, misspelling there. Initial condition or initialization u1 is equal to 12. Always put that in. The next one is a bit trickier. No, it's not really. Sorry, it's the Let's look at the adjacent differences here. 3, 7, 11, 15. The difference between each case is 4. That's actually what you sort of spot there. Like, what's the difference between each case there? So can you make out a pattern? And here it's essentially that the previous value was you just add 4 to the previous value. So here in this case, u of n plus 1 is equal to u of n plus 4, and again initial condition u1 is equal to 3. Okay, so that's a couple of quick remarks on recurrence relations. So we didn't actually end up doing anything about proof by induction, but we probably get around to it yet. Okay,